Every year, billions of standard omega-3 capsules are consumed globally, yet cardiovascular disease remains the leading cause of death worldwide. Large-scale clinical trials evaluating these generic interventions frequently return null results. Despite the high volume of supplementation, population-level mortality rates show no significant change. This data exposes a clinical paradox. On the left, supplement intake rises. On the right, the clinical efficacy curve remains completely flat. Ingesting a nutrient does not guarantee cellular integration. If delivery fails, the intervention stops before reaching the tissue. This failure is not caused by the EPA and DHA molecules, which are essential for human biology. The breakdown occurs in the pharmacokinetics, the process of transporting those lipids from the gut to the cell. Relying on ingestion metrics alone leaves a patient's actual cellular architecture unchanged, even when they are fully compliant with their daily dosage. Many patients attempt to reach their omega-3 targets using plant-based precursors like alpha-linolenic acid, or ALA, found in flax seeds and walnuts. However, plant-based ALA is a raw precursor. For the body to utilize it, it must be converted into the final EPA and DHA structures required by human tissue. This reveals a metabolic bottleneck. Plant-based ALA and omega-6 compete for the same conversion enzyme, funneling into a single choke point. Because the modern diet contains extreme excesses of omega-6, the pathway floods. The sheer volume of omega-6 physically blocks ALA from advancing. External factors like psychological stress, excess alcohol consumption, and glucocorticoid steroids further impede this process by depleting the enzyme's necessary cofactors, specifically zinc, magnesium, and B vitamins. Without these nutrients, the entire conversion process stops. Relying on plant precursors in an environment saturated with omega-6 is enzymatically incapable of achieving an 8% cellular index. Standard fish oil supplements present a different failure. To concentrate active ingredients and lower costs, most manufacturers use a synthetic molecular structure called an ethyl ester. Once extracted and isolated, these marine lipids become highly volatile. Their stability is tracked by the Oil Stability Index, or OSI, which measures how long an oil can resist breaking down when exposed to oxygen. Inside the human digestive tract, unprotected lipids face high heat and oxygen. These conditions cause the EPA and DHA to rapidly disintegrate through lipid peroxidation. Within hours of ingestion, these oils warp into jagged, unstable free radicals. They break apart long before they can reach human tissue. The body's metabolic pathways identify these oxidized lipids as biological waste. They are aggressively repelled at the cellular threshold and flushed away. Supplementing with generic, unprotected omega-3 is counterproductive. Higher dosages simply increase the gross intake of unabsorbable metabolic waste. To understand how marine lipids should be delivered, researchers in 1971 investigated Greenland's Inuit populations who maintained low cardiovascular disease despite a high-fat diet. These populations consumed marine lipids in their natural state. In the wild, these fats are never isolated. They are naturally bound to protective organic compounds. Modern supplements fail because they strip away these natural chaperones during refinement. To reach the cell, EPA and DHA must be rebound with potent polyphenols. These specific polyphenols come from pre-harvest extra virgin olive oil, which contains concentrated antioxidants that mimic the protective architecture of a wild marine diet. These polyphenols act as a sacrificial antioxidant shield. They absorb the oxidative stress of the digestive tract, allowing the marine lipids to pass safely into the bloodstream while remaining fully intact. This molecular stability is required to bypass the blood-brain barrier. The brain's DHA transporter protein identifies the precise configuration preserved by the polyphenol shield before allowing the molecule to cross into the neural synapse. Utilizing a polyphenol shield fulfills the biological requirement for transporting marine lipids across the cellular threshold. Human biology evolved to operate at a 3-to-1 ratio of omega-6 to omega-3. Today, the clinical average routinely exceeds 20-to-1. As excess omega-6 molecules pack together, they forcefully compress the flexible lipid tails, causing the cellular wall to harden into a rigid block. This rigidity blunts receptors. Essential nutrients fail to absorb,
signaling molecules bounce off, and cellular toxins become trapped inside. Successfully integrated, protected EPA and DHA restore membrane fluidity. Once incorporated, they serve as precursors to specialized metabolites known as resolvins. Unlike pharmaceutical anti-inflammatories that bluntly shut down immune pathways, resolvins actively clear cellular waste and orchestrate the timely resolution of the inflammatory cascade. Generating these resolvins is the only way to clear inflammaging, the chronic low-level inflammation that drives genomic instability and accelerated aging. Modern medicine continues to rely on legacy lipid panels and cholesterol tests to assess cardiovascular health. However, data from the Framingham Heart Study reveals that 50% of sudden myocardial infarctions occur in patients with perfectly normal cholesterol levels. Cholesterol is a volatile metric. These tests measure circulating traffic in the bloodstream, which is easily skewed by a recent meal.
Clinicians bypass variables using the omega-3 index, measuring the percentage of EPA and DHA integrated directly into red blood cell membranes. With a definitive 120-day life cycle, this index provides an objective 4-month historical record of true lipid architecture. Reaching an index above 8% correlates with a documented 90% reduction in the risk of sudden cardiac death. Objective preventative health relies on molecularly stable protocols, verified exclusively by rigorous 120-day cellular indexing.